let's talk about higher order ODEs. We talked about the general form of a differential equation, an ODE, as x raised to m am into dy e raised to m derivative of y plus x raised to m minus 1 am minus 1 e raised to m by dx raised to m plus etc. plus x raised to 0 becomes a0. We need to be talking about not just higher order ODEs, we need to talk about homogeneous higher order ODEs. So what is meant by the homogeneous part of this? It simply says that if I put a value for y here, and I can extract the same thing here, for example, or in other words, f of a into x plus b into y is equal to ab f of x comma y. If a function satisfies this condition, it is said to be homogeneous. Same applies for the differential equation as well. Now, coming to the part of ordinary differential equations, if this part is 0, if f of x comma y is 0, then there is an easy way to actually solve this equation. In most cases, most homogeneous equations will satisfy will be of this form. Now let's substitute y is equal to e raised to m x, let's say. It's a problem solution. Let's substitute it here. So what does this now come down to? Implies that x raised to m, a raised to m, mth derivative of this thing, which gives different variable here, n raised to m. This is coming. Next is an m raised to n. Dx by dx becomes e raised to mx plus x raised to n minus 1, a n minus 1 into m raised to n minus 1 into e raised to mx, etc. plus a0 into zero. Now let's take out e raised to mx. E raised to mx into x raised to n, a n, m raised to n plus x raised to n minus 1, a n minus 1, m raised to n minus 1, etc. plus a0 plus 0. Suppose that these x's doesn't exist. That is, the simple equation of e raised to mx into an m raised to n plus an minus 1 m raised to n minus 1 plus etc. plus a0 equal to 0. Evidently, for this e raised to mx to be a solution, this has to be equal to 0. So we have a polynomial in M, nth order polynomial in N, P of M is equal to a n m raised to n plus a n minus 1 m raised to n minus 1 plus a0. So we'll have n solutions for M. Depending on the type of solutions we come across, there are three situations that you can be in. If let M1 be and M2 be the solutions of our polynomial as said before, and if M1, we'll encounter three situations where M1 and M2 are equal. If they are equal, then y1 will be equal to c1x plus c2 e raised to mx, where c1 and c2 are constants and m is equal to m1 equal to m2. Second case, when m1 and m2 are imaginary. If they are imaginary or they are complex in nature, then the solution simplifies to y is equal to e raised to alpha x c1 cos beta x plus c2 sin beta x, where m1 is equal to alpha plus j beta and m2 is equal to alpha minus j beta. So that's how for ordinary differential equations of second order differential equations, that is n is equal to 2, the roots will be of this form. And so they are imaginary, y will be of this form. And for any other solution, for any general m1, m2, m3, and n, these two conditions can be derived from the general equation c1 e raised to m1x plus c2 e raised to m2x, etc. c3 e raised to m3x. The last equation is one of the more important parts of this entire discussion, in that it gives a glimpse of what y can be. Most differential equations are solved or have solutions that include three functions: sine, cos, and the base of natural logarithms, e. This is because the derivatives of these three functions, more or less, of the successive iterations, come back to either one of these three. And so most solutions of differential equations will boil down to these functions. And so that concludes our discussion of the ODEs, homogeneous ODEs.